Testing. Let's start. This is not working. Can you all hear my voice well back there? Yeah, I'll do it without microphone for today. Yeah, it doesn't working. Yeah. So today we will gonna learn about a little bit of the symmetric encryption, but we will mainly focus on the block cipher. And before getting into that, let's do a little bit of recap about what we have learned for the last time. So we learned about the basic use of the cryptography, and then like the reason why we need a cryptography is like our communication channels are insecure by default, and then we need to have some of the measure that like we can securely communicate with the other end. So some of the good thing is that like if we can make any kind of the plain text, that any kind of message to deliver to the other end, making it look like a completely random number, and then the attackers might don't know about like what's going on there. So we learned the notion of the perfect secrecy, and then there are lots of mathematical background and then like a probability and that kind of theory. But the important theory, the implication of that is that, so if we can make the distribution of the ciphertext look like a distribution of the random number, then adversaries may not know if there's random number or not. And then that should be hold for a secure scheme. That should be hold for the no matter how many messages attackers would observe, that should be preserved. So that's the definition of the perfect secrecy. And then we learned about the one very simple but perfectly secure scheme, which is an XOR cipher. And then what XOR cipher does is like suppose you have a messages to encrypt. For example, we have 3 messages, 1, 2, 3, 4, 5, 6, 7, 8. So the messages are sequential. So even though the messages are sequential, if we draw the key from the uniformly random, so the uniform random here means that the drawing probability of like each number are all the same. So that's a very important property. So as I mentioned in the last lecture, so rolling 2 or 3 dice are not that uniformly random, because if you roll the 2 dice, then you will have among the 36 cases, you will have only 1 case of the 2, only 1 case of 12, while you will have 6 cases of having 7. So the probability to have 7 would be 6 times higher than like the 2 dots or like 12. So that's not the uniform random at all. So that kind of the randomness works for some of the board games, but it's not suitable for the cryptography. So we need to have like the very uniform random, and then like if we draw the random number from there and use that as a key, then we can apply XOR, then we can get the ciphertext. So on the right side, I drew a little bit of figures to demonstrate that how the distribution look like. So this does not encrypt the same number, but how I tried to show you was like I prepared the plain text from 0 to 100. So it sequentially goes up 0, 1, 2, 3 to 100, and then I draw 100 random number within the range from the 0 to 100, and then like I draw that using the Python's secure random. So it guarantees that like the random number getting the probability of each number is uniform. And then that result shows like the first one is 18 or something, second one is like 70 something, 60 something, and then near the 100, something like that. So that their distribution is somewhat random. But if we get the distribution of the XOR result, it would look like this one. So even though we have like the very simple distribution for the sequential plain text, if we draw the random correctly, then like we would have like this kind of the random behavior. So that makes that attackers may never guess what's the encrypted data, what the encrypted data is. But even if the XOR cipher is perfect, there are some of the limitations. So if we reuse the key, so the one challenge, the XOR is perfect. Yeah, that challenge demonstrates that like you can decrypt the ciphertext if the key was reused, and then if you know about what is the plain text or plain text ciphertext combo. Yeah, because the internal logic is very simple. If you apply it the same way, then you can easily get like what the key is. So that means that you need to have you should not reuse the key. And that means practically, suppose you want to send a 1 GB of video file to your friend or someone, then key must not be reused. So the key size must be the same as the data size. And then our communication channel at the start is not secure at all. So that means we need to have some of the way to deliver the key. And then the most secure way to deliver the key is like you guys can meet physically and then like write down the key. But to send the 1 GB of data, we need to share 1 GB of key. So in that sense, or then in that case, like just share the data by meeting the physically, right? Yeah, that would be the better approach. And then I know that there could be some of the use cases of this kind of thing. For example, if the 1 GB of the data is not available today, then today you guys can share the key first, and then later after downloading that 1 GB of the video, then we can send that using the key. But in many other there could not be like many practical reasons to use this kind of the encryption in reality. Yeah. So the implication is that even if some of the schemes are perfectly secure, there are several reasons that we cannot use that in reality, and then that is not that efficient when we encrypt the data. So then let's think about somewhat ideal world. So we cannot reuse the key, but what if we can share a random number generator between two entities? So what that means is that, so suppose they're a random number generator. Yeah. So this is jar, and then we can draw a random number for multiple times, almost infinitely. Yeah. And then suppose we can physically meet and share this random number generator, not the 1 GB of the key. If that generator is smaller than 1 GB, then yeah, it's quite efficient to send, then use this as a random number drawer and then send a huge amount of data. So what we can do that in this case is we can share the random number generator. And then the property that it should have is that it should spit out all the same sequence for the drawing trials. So suppose the user A draw the random number for 5 times, and then at the user B's side, the resulting number must be the same. Otherwise, we cannot correctly decrypt XOR cipher, right? So if we can share a random number generator between two, something like this, then we can securely use XOR cipher, something like encrypt message 1 with this key, message 2 with the second one, message 3 with the third one. And then on the other end, we can also get the random number sequentially and then apply that for the decryption. Yeah. So it'll be perfectly secure. Yeah. So if we can share this kind of the random number generator, then we can use one-time pad XOR, a simple scheme, to be perfectly secure. So cryptographers in early days, they tried to design this kind of the random number generator, shareable one. So that's so-called stream cipher. Yeah. And then the thinking was started from like because Shannon, yeah, that guy proved that XOR cipher one-time pad that's perfectly secure in like the 1940-ish or something. Yeah, 1950-ish. Yeah, it's quite early, but there was no way to share the random number generator securely between two entities. So after that, like there are some of the advances in the like cryptology, and then cryptographers try to create those ones. So there are many algorithms for the stream ciphers, but the most frequently used one was RC4 and RC5. Yeah. So like the none of the document directly says that the etymology of this crypto, but the so do you guys know the Ron Rivest, the inventor of the RSA algorithm? Yeah. So that guy developed the RC4 and RC5. So we have a conjecture that the Rivest Crypto 4, Rivest Crypto 5 for this algorithm. And if you are interested in the details of the algorithm, you can visit the Wikipedia articles stated here. But you can think it as like these kind of algorithms. What this kind of algorithm is doing is that, so the two entities can physically meet together, and then they can share the variable length key. So from 40 bits to like the maximum to 48 bits. Yeah. So like a maximum 512 bytes. So it's quite short. Or like it could be like a 128 bytes, just 16 bytes, 128 bits, just a 16 bytes. So the sharing that kind of short message physically is quite easy and then not that burdensome. Yeah. So that's the intuition. And then suppose they share like this kind of the same key. So this is so-called as a key because like this number will determine what kind of the sequences will be generating from these kind of algorithms. And then after agreeing, two parties are agreeing on the key, they can use the same algorithm, and then these algorithms are public. The only secret thing is the key, this short number. Then they can run it, then they would have like the same sequences are generating on both sides. So in that case, we can do one-time pad on top of it. Yeah. And then because one-time pad is perfectly secure, and the scheme might be secure. Any questions up to this point? Yes.
You said that this only works with like small messages.
So one-time pad requires the key size need to be the same as the message. That's the caveat. But to do that, we need to prepare like a long key for the long, like the plain text. But to remove that kind of restriction, what if we can have like this kind of the random number generators based on the key? Then like if our key, our data length is 1 GB, then run this algorithm for multiple times up to generating like the 1 GB of the random number. Yeah, that is the point. Yeah. And then the reason why I introduced stream cipher, while the title of this slide is the block cipher and symmetric encryption, is that because this is insecure. There is a question from Zoom side. If we are using XNOR instead of the XOR, are they having the same complexity for decrypting? Yes, definitely true. Yeah. So like no matter what kind of operation you do, if the operation is like the addition like operation, then like the complexity will be the same. So the generalized version of the XOR in Cipher is a one-time pad, and then using XNOR or add or subtract, yeah, that these are all fall into the one-time pad. So like the RC4 and RC5, they are debunked as an insecure algorithm. And then like you can also find all these kind of the details in the Wikipedia article. And then for RC4, as of 2015, there's a speculation that some state cryptologic agencies, they did not disclose who it is, but maybe some of you can make some of the conjecture about who can decrypt the thing. So that they says like suggest the capability to break RC4 when used in TLS protocol. So that we will learn about what is the TLS protocol in later part of the in the course. But yeah, TLS here means that the transportation layer security, and then that is used by default whenever you are connecting to the website. So what that means is that some state cryptologic agencies can decrypt whatever message you are securely communicating with the Facebook or Gmail or that kind of the servers. So it seems very dangerous. Yeah. So the Ietf, so Internet Engineering Task Force. So what Ietf does is like the Ietf has lots of RFCs. So the RFC here is a request for comments, but what this means is that like it has a lot of the document with the numbers, and then it defines what kind of technology should be used or should not be used, or what kind of the engineering practices must be done in the internet to make our internet too robust and secure and available, those kind of things. So the RFC 7465 means that like it is archived in the internet standard to not use RC4 in TLS. Yeah. So the important thing here is that the RC4 is insecure. And then even for RC5, the enhanced version of the RC4, there is a crypt analysis. And then crypt analysis here means that like try to get the lower bound to break that kind of the crypto scheme. Yeah. So if that lower bound is difficult enough, then you can trust the crypto scheme because nobody else can break that crypto scheme less than like that kind of time complexity or something. Yeah. So the crypto analysis says that like the 12-round RC4/5 is susceptible to differential attack by using 2 to the 44 chosen plain text. So the 2 to the 44 is like the 16 tera number of the messages. So it seems to be quite big or a huge number, but in terms of like the supercomputer scale, so in these days, the 2 to the 44 is not that big number at all. Yeah. So in that case, like what this sentence states that the RC5 is not secure in current error. Yeah. And then the reason, yes, question? Yes. So like the 2 to the 44 means that like the lower bound for the brute force attack to like with using the chosen plain text attack is like it requires like as low as like a 2 to the 44. Yeah. So like that means that their lower bound is quite low than like our supercomputing power. Yeah. So the reason why these kind of the crypto scheme is insecure, and then like the later like the analyzed as like the weak, is that like this kind of scheme does not have mathematical proof. So what that means is that like the cryptologists, they are working hard to make a proof to provide a proof that the lower bound cannot be lower than a certain point. And then if that is big enough than our supercomputing power, then we are secure. So the cryptologists, they are working hard to get that, but these kind of the cryptography is not with that kind of proof. So that's why there could be an attack like these two. Any questions? So then let's move on to the block cipher. Yeah. So the block cipher is a cryptographic scheme that only encrypt fixed size message. So think about XOR cipher. It's general. So if the message length n, what we need is like just to get the length n key. So it is not restricted by the message length, but the RC4, RC5, we can also generate like a long random number based on that algorithm. So there's no restriction. But in the block cipher, cryptographers restrict the model as to encrypt the fixed size message. And then in practice, right now, the advanced encryption standard, AES, they use a 16-byte, the 128-bit as a block cipher, a block size. And the reason why having such a restriction only to 16-byte is that restricting the size, it does not open the problem to the like a totally open space. It will be restricted into just a 16-byte message to the 16-byte message mapping. So the restricting the size simplifies the getting the mathematical model for the cryptography simpler. And by having some of the simpler model, cryptographers can provide a proof that the attackers can never go for the lower bound for breaking the crypto at certain level. And then for the perfect secrecy means that the attackers should never distinguish a ciphertext from a random number. That's good, but that's too strong. And then having that is practically infeasible without having the same length to the same length key to this message. But in this case, we do not have that kind of guarantee. But the guarantee that the cryptographers will give is that the chance of the attackers, they can distinguish a message is not a random number at all, is 1/2 to the 126. So 2 to the 126 is a super big number. So that without having that kind of trials, attackers cannot meaningfully attack the crypto scheme. And then interesting thing is like the previously RC4 and RC5, they do not provide that kind of proof, but in the block cipher, cryptographers can build some of the proof out of it. And then if one is mathematically proven, then that will never change. So that's why it's good. And then as a security researchers, we would like to use that kind of the secure scheme that has a strict lower bound, that the attackers, nobody else can go lower than that for attacking the crypto scheme. And then how the block cipher would look like in conceptual figures are as follows. So here, a block means a fixed size message. And then for a message M, suppose I prepare the message as a CS370 16-byte message, and it looked like a flag. It's exactly 16 bytes. And then like if we change this as a hexadecimal number, a 128-bit number, then it'll be this. And then, so CS370, something like that. And then block cipher requires a key. So the key need to be shared secretly between the two parties. And then the requirement for the key need to be short, because for the convenience of the key, having a key sharing. So we all felt that like sharing 1 GB of key would be painful for like sending the data over the network later, right? So that's the requirement for the key. And then block cipher, it will transform this message based on the key. It will shuffle the thing into somewhat looking like a random number. So this is how the encryption works. And then the decryption of the block cipher is working as an inverse function. So decryption works in backward. So important thing here is that the block size and is fixed. So for example, here is a 16 bytes. Then the message size should be 16 byte. And then also resulting encrypted ciphertext size is also need to be in 16 bytes. Because what block cipher does is like it will actually creating one-to-one onto mapping between the two 128-bit integer space. And then it's something like shuffling the thing based on the key. So the decryption works in opposite. So there's a question. Pardon? So we will learn about that part later. in next week. Yeah, so that there is a key exchange algorithm. Yeah, when we get to the point to the using a public and private key and then key exchange algorithm, then we will learn about how we can securely exchange the key over the network. But in this case, I'm assuming that to securely exchange the key, we need to meet in person, and then I can speak into your ears. Yeah. So the decryption works in completely opposite. So I just told you that a block cipher in this case is so from the 128-bit space, it's just a one-to-one onto mapping, the bijection mapping to the other set. So it will have the same size, and then that means that we could have an inverse function. So the cryptologists designed the block cipher in that way. So the decryption means that we need to provide the same key to have the same kind of the mapping. And then if we supply the ciphertext as an input, then we could get the plain text as an output. But the algorithm is not exactly the same. Yeah. So it should run the forward running of the encryption algorithm, and then the decryption runs the algorithm in backward. Yeah, to get the correct value out of it. Yeah. Any questions about the concept of what is the block cipher? So you can think it as just a 16-byte encryption and decryption. Yeah. And then what does the block cipher do? So conceptually, it generates the permutation of the numbers. So the permutation is something like you have the set of the number, and then it's something like shuffling the card. Yeah. And then if we have the identical set of the card, and then if we get the numbers 0 to the first one, 1 to the second one, 2 to the third one, and something like that, then a two-party can agree on the same sequence for the mapping. So for example, if we shuffle the sum of the bit space and the block cipher well with the key, then if we supply 0, then it could be mapped into the sum of the totally looking random number like this. 1 could be mapping to this kind of thing. But this kind of the permutation is determined by the key. So the selecting the key is you are shuffling the card. Yeah. So for the advanced encryption standard, we will learn a little bit of later, AES, yeah, they use 16-byte or 32-byte keys. And then that key determines how the numbers will be shuffled. But if the key is the same, then based on the algorithm, we will have the exactly same sequence. So if the two ends share the same key, they will see the same sequence. Yeah. So based on suppose we have 4 different keys, key 1, key 2, 3, and 4, then we will have a totally different sequence are coming from the encryption block cipher algorithm, if that is well designed. Yeah. So even if the messages are aligned sequentially, the ciphertext does not look like a sequential at all, and then it would look like a totally random number. Yeah. Then how can you use this kind of block cipher? So let's get back to the same situation. You want to communicate to the other securely and privately, then physically meet first, and then securely exchange this 16-byte key. Yeah. Then suppose this guy wants to send number 3. Let's meet at 3 p.m. at the local boys to have a late lunch. Yeah. So to short that message, suppose that is the number 3. Then we will put the number 3 to the block cipher. But I told you that we should encrypt the 16 bytes so that we can pad it a 0000003 or something like that, making it as a 16 bytes. And then using the key that we exchanged previously, yeah, run the block cipher algorithm to get the encrypted number. So it will generate this kind of number, and then we send this over the network. Then the other guy has the same key. They run the inverse of that one, the block cipher, which is a decryption function. Yeah, and then put the encrypted text here then it will output 3. Because the key is the same, the shuffling of the numbers are exactly the same. That's why like the running the inverse function will like make the ciphertext to be a plain text. So they can know this is 3. And then conceptually, what it does is like the algorithm, although it is an algorithm, so we don't have the data, we don't have to store the huge amount of data, but having the algorithm and the key means that you can obtain this kind of table that which one maps to the which number. So conceptually, whenever you want to encrypt the 3, then there's a corresponding ciphertext, you need to send that. And then whenever you observe that this number, then you can just use the table in backward. So try to search this number, and then that is on position 3, then the plain text message will be 3. So you can think it as like the setting the key in the block cipher is shuffling the kind of the order. So that's why it is called as a permutation. Yeah. And then this is the time for like the attacker comes in. So the attacker does not know the key. So even if they know that like what kind of algorithm, so for example, AES for the block cipher, they know about like these two guys are using that because the attacker don't know the key. The attacker cannot decrypt the message. Yeah. If the block cipher is well designed, yeah. But there is a chance that the attackers may try some of the so-called brute force attack. So suppose the attacker may heard like the part of the key or something, and then they may try to match the key by their own. Yeah. So that there always a chance that the attacker may guess the key, but our key selection was 16 bytes. That means like it's a 128 bits. Then like the attacker should try all the 2 to the 128 times to get the correct key if there's no like a prior like knowledge for the key. Here's one question. So that's a very important question. So even if like they decrypt this kind of the random number, it could fall back into 4 or 5. Then the attacker got confused that whether that is plain text or not. Yeah. So to correctly know that like this is the right decryption or something, then like the attacker may have knowledge of like the correct message. So for example, so the example that I used in the last lecture was like that I'm always saying hello to like some other people, right? Then if the attacker knows that the first message should be hello something, yeah, then they can prune out some other cases. And then like if they have multiple messages, and then if they have like the assumptions that I will only use English and number characters, then like if the sum of the characters are not decrypted in like that character, yeah, then that could be another signature. And then also like even if like all the character space are correct, if that is like a sane in English and then matching to the grammar, so that kind of thing would be another evidence that like we can guess about like a correct key or not. Yeah. Any other questions about like the usage of the block cipher and then like the attacker model here? Yes.
Does it use the XOR?
So internally, it uses shift, XOR, add, subtract, that kind of information, the thing. But the important thing here is that like adding 2 numbers will generate carry. But if we ignore that, then we have a loss in information. And then subtracting 2 numbers, and then we also having loss in some of the operations. So what that means is like A minus B equals C. So even if we know C, like we cannot go back to A and B. Yeah. And then whenever there's an information loss, we cannot build the inverse function. So the block ciphers must have an inverse function. Otherwise, we cannot decrypt it. So the block ciphers internally use a lot of XOR because XOR is not losing any kind of information if you have a value that prior to that. Yeah. So like based on the key and the ciphertext, or a key and the plain text. They chain XOR and shift and then rotate the bits each other, yeah, to try to not lose any kind of information, but still making the output bit pattern as completely random. Yeah. Then I will move to the next. So like we just assume that the block cipher is secure, and then if that is secure, then it works like that. So the important thing is like the how we can make the things secure. Yeah, and then that's the cryptographer's job. And then I borrow some of the terms from the cryptography class to give you a little bit of idea of like the what's going on in there. So we call the theoretical model for the block cipher as a pseudo-random permutation. And think about it. So what we want to have the property is that like whenever we encrypt something, so it's just a permutation. So my number will be permuted and then mapped into some other number and the encrypted ciphertext. And then what we want to have some of the property is that like that should look like completely random number to the attacker. Yeah. So that we can actually do that if we have a random permutation. So the random permutation here means that it should be perfectly random. Yeah. So they're not generated by algorithm at all. Yeah. So that's the very ideal model. But the problem is that we cannot have that kind of ideal random number. So I believe it's physically possible if we use the quantum physics. There's a quantum entanglement, and then if we share the entangled qubits and then like open the qubits, then like we will share the sum of the thing. So that's the so-called quantum key distribution. So that's a very advanced technique, and then it's somewhat available in some countries. They do enable the kind of key exchange and like cell phone communication, but we don't go deep like that. Yeah. So in our case, so and then that's very expensive. So like it's practically infeasible to have the real true random permutation in reality. Yeah. So what cryptographers are doing that is they are trying to define an ideal model, so-called pseudo-random permutation. So it's not random. It's something like random. So that's why it's called so-called pseudo-random. And then pseudo-random here is that the random generation of the random would be totally uniform. So like it does not have weaknesses about some of the having some permutations are occurring more than the others. Yeah. So it's engineered random for that. And then by using that kind of the pseudo-random property, cryptographers define the pseudo-random permutation. And what that means is that a well-designed pseudo-random permutation should have the attacker's chance to distinguish a permutation is different from the true random permutation. It should be extremely low. So it's similar to the perfect secrecy and then practical security kind of the thing. Yeah. So we cannot have a true random permutation, but if the engineered pseudo-random permutation, it exhibits the behavior like the attacker's chance to correctly guess this is not a random permutation at all. Yeah. And that is extremely low, then we can say it's secure. So the same thing, if we have a lower bound, which is so high computational complexity, then we can currently compute with the supercomputer, then we can assume that we are secure at this point. Yeah. So for example, advanced encryption standard, yeah, they do have the crypt analysis, and then the best analysis says that like that there is a bi-click attack. Yeah, I don't know about the details, but the implication here is that attackers may break it with the complexity of 2 to the 126.1. And that's the 1 over 2 to the 126.1 is a very low chance. And then let's take a look at how difficult it is. So the 2 to the 126.1. So this is a big number. So this is 9.11 something multiplied by 10 to the 37. And then right now, our Intel or AMD or ARM CPUs, they are equipped with the hardware accelerator for this kind of the encryption features. So if we implement the encryption purely in software, then that could be slow. So the CPU designer inserted that kind of feature around the 2012, 13. Yeah, it's quite a recent feature because we all use the encryption for the most of the cases for the internet. So they implemented in hardware. And then to get the entire 16 byte of the block, yeah, the CPU requires around 20 to 30 cycles for the Intel's one. So Intel's AES and new instruction set, yeah, that is the fastest one. But even for the fastest one, it requires 20 to 30 cycles. But let's assume that there is a CPU in one clock cycle. They can calculate the AES for one round or something. Then right now in these days, we have around the 6 gigahertz of CPU. That means the 6 billion instructions can be processed in 1 second. Then this number divided by this, then we can calculate how many seconds do we need to break that crypto. And then that's this amount of seconds, and then divided by some numbers, then this amount of years. And then even if you have 1 billion of such computers, we can remove 9 zeros, then it's still in several trillions of billions of the years. So that means that with that high lower bound, we can ensure that our current AES is secure even against the fastest supercomputer in the world. Yeah. Any questions up to this point? Yes.
So you mentioned that process
Yes.
before that, were things just filling its computer or web browsers or resource something before? How do you go about that?
So it's not about the security point of view, it's more about the performance thing. So before having the AES new instruction, so it's so-called AES NI in the CPU, so that they don't have such instructions. So we need to compute all the things in software. But think about it, in my computer, calculate everything in software and send it over. So the same encryption was applied. So there's no security issue, but the only issue was the encryption and decryption speed was slow. But that was not that matter for the end users, because think about laptop, yeah, that time is the several microsecond or something for the encrypting the short message. So it's not that problem, but think about how the server will fill that. Yeah. So there is a paper. So there is a network measurement paper called the cost of S in HTTPS. So what that means is that when you connect to the website with HTTPS, that automatically applies the encryption with the TLS, transportation layer security. And then for the servers who don't use HTTPS, they don't have to do encryption. So in the era that we don't have a hardware accelerator, that cost was quite huge in terms of power consumption. Yeah. But after having that kind of the technique, that kind of cost get reduced down. So now we recommend all website should use must use HTTPS, and then we can do that without worrying about spending more money for sending the traffic. So one question from the Zoom, do quantum computers pose any threat to block ciphers now or in the future? So I will describe a little bit about how quantum computers are threats to our current era crypto in the public key crypto lecture. But as far as I know, the quantum computers cannot break current AES. So if you're searching for some of the needs to document or some of the recent newses, so there is a consortium to decide the so-called post-quantum cryptography. So what that means is that even if we have a quantum computer, are there any secure schemes? there are secure crypto schemes that we can use. And then that actually does not need to have the quantum computer right now. So all the computation can be done with the traditional computer, but the term post-quantum crypto means that we would like to design a crypto scheme that is secure even if there's a quantum computer. Yeah. And then in doing that, they are searching for key exchange algorithm and public key crypto, and then digital signature algorithms. And this is because right now we are using the RSA or the ECDSA, elliptic curve digital signature standard. Yeah. And then those algorithms are based on the discrete logarithm. I will describe the discrete logarithm in the lecture for the public key cryptography. And then that specific operation is weak against the quantum computer. So that's why the quantum computer can break a key exchange algorithm and also for the digital signature algorithm that we are using currently. But that is not applied to the XOR shift based like the block cipher algorithm. So NIST is not like the searching for the block cipher to be a post quantum because they are already post quantum. Question?
If they have 8 yes, 1.8 is very secure enough, why is the 256 AES recommended?
So in the most of cases, we still use AES 128, but our computing power grows somewhat exponentially. So have you heard about the Moore's law? Yeah. So many believe that Moore's law was saturated like this, but recently it goes up again. Yeah. And then with the rise of the huge computing power is required for the AI and the processing of that. Yeah. So the CPU and the chip designers, they put a lot of money to evolve their semiconductor technologies again and again. So the reason why we have 192, 256 bit lengths of the key is even if that time reaches, then we could go ahead for we could be how can I put it? We could increasing the lower bound, yeah, to that point. Then we can keep the thing secure, yeah. And then let me do a little bit of summary. The lecture is not ended yet, so don't get misled about this slide. So let me give a little bit of summary about the block cipher. So it will be great if we can agree in a short key and then reuse that key for encrypting the longer message. Yeah. So the drawback of the XOR cipher perfectly secure. The drawback of that one was we should have a longer key. Yeah. But the stream cipher was designed to have some of the magical thing, the random number generator shared among the two parties. But the problem of that approach was it's very hard to give the mathematical proof. So these were broken in reality. So cryptographers designed the block cipher, and then block cipher has a restricted model. So encrypting just one block to the other block. But by doing so, they can reduce the model as a simpler one. And then that's why they can provide some of the proof. And then the goal of the block cipher is that if they would like to build a so-called pseudo-random permutation. So the permutation that they made with the specific key should not be distinguishable from the attacker. And then for the current AES, so we have the 120.6.1 for the 128 bit of the key. So ideally it should be 2 to the 128, but a little down, but the algorithm is good enough to set the lower bound as a 126.1. Yeah. Any questions? Then I will move on to the next about the little history of the block cipher. So I mentioned about the AES because I do not wish you to memorize the DES at all. Never use DES because it's insecure. But as in history of the block cipher, I want to introduce that. So there is an algorithm DES, and then it was developed in 1975 and then standardized in 1977. Yeah, it's quite an old algorithm. And then you can see that there is a key. Key should be 64 bits. And then there are some of the shift operations, and then XOR, shift XOR, those kind of things. And then it will shuffle the bits in multiple around based on the key and the plain text. Yeah, and then it will generate some of the output as a ciphertext. But this algorithm was developed by IBM. So the IBM in that era was like a Google. Yeah, in this era, like they develop almost everything like that we are using for computers in that era. Yeah, and then like the crypto scheme was developed by IBM, but later it was adopted by the Federal Information Processing Standard, FIPS. So if you're working on the security sector, you will see a lot of like a FIPS 140, that kind of numbers, and then like this institution, yeah, chooses like what kind of security technology the U.S. federal government must use to have the secure communication and then protect their infrastructure. Yeah. So it is commercially developed by IBM, but they adopted as a standard and then like the release as a free use. And then the interesting thing is that the original design says that the key length must be 64-bit, but interestingly, the key size later changed to 56 bits, but while keeping the block size and ciphertext size as like this same. So it is very weird for the block cipher because for a block cipher, because the block size is fixed, we can have the key size at least for the block size. Yeah, that's the secure composition. But why the key size is 56 bits? Let's get into more about that kind of thing. So 64-bit brute forcing, yeah. So the trying everything for the 2 to the 64, it's like the 120 peta trial or something. Yeah, that was super difficult in 1977, 80s, 90s. Yeah, that was not possible. And then they intentionally use a shorter key, so 2 to the 56-bit key. But in January 1999, there is this foundation called the Ietf. So it's an activist foundation, like who wants to protect our right to have like a private communication kind of thing. So I really like this kind of thing, entity. Yeah, the fight against the freedom in like the communication and privacy kind of thing. And then what they did is like that they demonstrate that like that they can publicly break any kind of the DES encryption if it is given in 22 hours and 15 minutes. So what they did is like they tried every like a possible key space and then reveal the key. Yeah, and then that was possible. Yeah, in 1999. Then if it was 64-bit, then it could not be broken in 1999. Then why? The key size is 56 bits. There are very interesting articles inside of Wikipedia. So the US Senate Select Committee on Intelligence, so it's part of the US government, reviewed the NSA's actions or something like that, and then they revealed what NSA have done to the crypto scheme. Do you have a question?
Yeah, didn't the NSA also make an elliptic curve and they like already know, like knew how to break it, but they handed it out?
Yeah, that's right. Yeah. So there's some state government, nation state government does that kind of thing. Yeah. So that I just want to teach like that kind of activity exists. Yeah. So we should be very careful on choosing the security technology because like some of the entities looks benign, but try to implement some of the backdoors to making easy to like decrypt the people's data or something. So what's archived in here is that NSA convinced IBM to have a reduced key size. Yeah, and then they did not tamper with the algorithm or like the block use or some other thing, but what they did is like the NSA tried to convince IBM to reduce the length of the key to the 64 to 48 bits. Yeah, they even like wanted the super weak algorithm because they want to decrypt the thing. And then to try like that kind of thing, we need a supercomputer. And then US government, yeah, they can easily get the supercomputers. And then I believe the world's fastest supercomputer is now in China. Yeah, so that there could be some of the battles between the nation state to decrypt this kind of the crypto. Yeah, that could be possible, but that they would like to make it 48 bits, maybe in 1970s, 80s, like maybe the US government's power was like decrypting up to that number of the bits. But thanks to some of the engineers to the in the IBM, they increased that to 56, but I don't fully thank to them because they were compromised to get the key length reduced to not the 64 to like the 56. Yeah. And then here I want to teach a little bit of ethics. So if you graduate and then work for the security engineer or something, yeah, please do not be compromised in that kind of request, and then make the world secure by applying the best technology that you can choose for that. So the implications here is that the key size determines the strength of the block cipher. Yeah. So if the algorithm is well designed and then having a proof that it will work as a pseudo-random permutation based on the key. But using a smaller number of bits than the key, yeah, will make this cipher will be easily broken by the brute force attackers. So 64, 56, and then the 48 bits, right? And then the brute force attack here means that trying all the key space for the block cipher, and that's the one thing. But if there's a crypt analysis is provided, for example, for RC5, no matter what kind of the key size you have, there's a 2 to the 44 attack on it. Then the attacker can only run that number of amount of computation can break it. And then 2 to the 56 was broken in 1999. Then 2 to the 44 can easily be broken in this era. So that's why we should not use RC5. Yeah. So we use AES, so Advanced Encryption Standards. So it developed to replace the data encryption standard made in the 1977, because the EFF broke DES in 1999. And then how do they break the encryption was, so they designed a special hardware, so-called deep crack. Yeah, the name itself is very explicit. Yeah, and then they designed this kind of chip, and then having a multiple chip as an array. So it's something like the crypto decrypting the supercomputer kind of thing. And then they run that for 22 hours, and then like that. I believe the entire cost of the building this kind of board is less than $1 million or something. Yeah. So by using that kind of the small cost, yeah, then they can break all the crypto in the world, and that's super problematic. So the world need a more secure encryption. Yeah. So AES, yeah, it will have the key size, variable key size, 128, 192, 256. So its block size is 16 bytes. So 128 bits. So that's why the smallest possible key size is 128. And then right now, most of the encryption uses AES 128 because our supercomputers are not there for breaking that yet. And then having longer key size means that we need to have a more round to running this kind of the shuffling. So that means that we need to take more time for for getting the encrypted data for longer key. So for the performance reason, we use the shortest but securest possible key, yeah, for now. But the AES is designed to be extensible. So wherever the supercomputers catch up, some of the computational power, then we can change the key bit size to this and that. But after that, we might need if the supercomputer can break can go up to the 180 or something, then before hitting the 200 to 250 something, yeah, we need to move on to another algorithm, but that time is not coming soon yet. Yeah. And then this is So like the reason why I exampled like a 16-byte block and the block size is because like the AES uses that. Question?
Computers catch up to break AES into 56. I think using AES 5 would not be enough.
So AES is not designed to have a 512-byte bit key, but it could be extended. Yeah, but doing that requires another round of like mathematicians need to give proof and then all the things. So that right now AES is with the proof with the like the 256 bits of the key. Yeah, but the algorithm can easily be extended, and then like the mathematicians can also provide the proof like that. So maybe I'm not sure about the decision of the world best cryptographers about like what will they do when that day comes in. But it could be AES 512 or 1024 or something like that, or using the completely different algorithm for that. Yeah. And then how can we use the AES encryption? Yeah. So suppose we need to encrypt the 16-byte block. Yeah. Then what we will do is conceptually, we are wrapping the encryption function over message. So what that means is that for a specific key, we provide a message and run encryption, then we will get the 16-byte encrypted data. Yeah. And then decryption is running the algorithm in backward to get an inverse mapping. So we can also think that decryption as applying the decryption function over encrypted data, and then it will get M, and then for the specific key, because key will determine how the numbers will be permuted. Yeah. And then sometimes we write the decryption function as the inverse of the encryption function, inverse -1 as a superscript. The reason is like that's exactly the inverse function to mapping from here to there. Yeah. Then I keep talking about the 16 bytes. Then you might curious about like can we encrypt the blocks that the message size is less than 16 bytes? Yeah, that's yes. And then we have somewhat standard for doing that. And then we can do that by adding the padding. But think about the case. So suppose we just want to encrypt the number 3. That's 03 is 1 byte as a 1 byte. But if we make a padding as the 03, 0000000 as like a 16 bytes, then can we distinguish that from 1 byte to 3 or 16 byte to 03, 0000000? We cannot distinguish that. So to make it explicit, so there is a block scheme, so-called ECB, Electronic Code Book. So electronic code book is a padding scheme to make this kind of a block cipher can encrypt any size of the messages, not just for the block size less than 16 bytes, but for the blocks, like a message size bigger than the block size. So for any arbitrary size message, we can use block cipher for multiple times. And then at the end, there could be some of the block that may not have 16 bytes. So if we can encrypt that correctly, then we can handle like the arbitrary sized block, arbitrary sized message with the block cipher. And then how ECB works is to pad the length of the padding as the byte for the length of the padding. So like you might not get like what these word means. So I prepared a diagram. Yeah. Suppose you have 15 bytes of the data. From 0 to 9, that's a 10, and then A, B, C, D, E. So it's a 15-byte string. Yeah. So if we want to encrypt this data, then from position 0, we will have 0, 1, 1, and then 9, 9, and then position 14, we have E. So the position 15 is the 16th byte because we started from 0. Then at here, we add the padding. And then padding is just 1 byte. So we add 0, 1, the number 1 as a padding. Then how it works for the 14 bytes data, is, so it has 14 bytes. So we have 2 remaining bytes. So we put 0202 twice for 13 bytes. 030303. So the length of the padding for the length of the amount of the time that required for the padding. Yeah. So put that in that amount. Then suppose you have a 1 byte of the data. Then we will put the plaintext here, and then we need padding for 15, number 15, padding length as a 15. So 0xf is 15 in hexadecimal. So we've stored that for 15 times to make a block. Then what we can do is, after decrypting some ciphertext, if we get this message, then we can take a look at the last byte. And then if that says 0f, then we need to count 15 of the 0f. Then we withdraw it. Then we know that this is the only plain text. The same thing works for this one. So last byte is 03. Then we can remove last 3 bytes, and then we need to check all last 3 bytes are 03. Otherwise, it's an invalid scheme. Yeah. Then we can take the plain text like this. Then you might be curious about if there's no padding required. So what that means is that, so encrypting 15 byte string will be something like this. So we will put 01 as a padding. Then what if we would like to encrypt the same amount of data, but the 0x1 as the plain text? So this is a 16 byte encryption. Then if the 0x1 is the plain text, we cannot distinguish it, right? So to avoid that case, 16 byte block should have 16 byte of the padding. Yeah. So it looks silly, but it is required to distinguish whether the padding is the padding or which part of the thing is the plain text. Yes, question?
So in every case of encryption, you will have padding. So never be sure you don't have padding. So like
that's right. Yes. So the bytes less than 15 bytes of the up to 15 bytes of the encryption, you will get 16 bytes of the result. But if you encrypt the 16 byte block, then you will get the 32 bytes, because the rest of the 16 bytes, that tailing one is completely the padding. Yeah. By doing so, we can always detect the padding. Yeah. And then because of the padding exists, we know that the exact size of the plain text. Pardon?
Like the null character and C, something that tells you to stop.
Yes, something like that. Yeah. That's right.
Is the pattern all the same character, or is it random as well?
So in the definition of the Ecb, how the block cipher works, yeah, they are defined as all having the same size as the length of the padding. Yeah.
Well, I'm saying the individual padding, each bit, is it the same?
Yes, it should be the same. So same as the length of the padding. So that's why for the 16, we all should have the 16 like this.
What I was asking is when you're setting off the padding, is it all padded with zeros, or is the padding itself random as well?
Padding is not random at all. The padding is this one.
So it's going to be all the same.
Yes, all the same. But it will be encrypted, so you cannot detect it as the attacker who don't know the key. But you can assume that the last block may contain the padding, but you might don't know how many bytes are padding, because you cannot see the plain text of that value. Yeah. Then the next one is so how can you encrypt the 2 blocks on the block cipher? So for example, if we want to encrypt this, and then as a padding, we also need to encrypt that. So for the first round, we will run using the same key. Yeah, we will put these kind of the message, and then get the first 16 byte. And then we move on to the next 16 bytes, encrypt these, and then get these kind of a result. And then we concatenate 2 and then send that. And then decryption is the same. So we will apply decryption per each 16 bytes using the same key and then decrypt it. And then we will get the plain text. And then from the end, we will check the padding and then we will get the message size correctly. And then can you get that like in this scheme, we can encrypt and decrypt arbitrarily sized data. Yeah. So then no matter how long it is, 16 by 16 by 16 byte, and then add the padding. That's it. So for example, if there's a 32 bytes string like this, then add the F like that. I just make it as a palindrome. Yeah. So how can we encrypt this? Is like they encrypt this first, and then this next, and then there should always be padding. So the padding size is 16 for this case. So we also need to encrypt padding. So the encrypting result will have a 48 bytes. And then if there's another byte, then like a padding will be Q and 15 of F, something like that. That's how it works. Any questions? Yes.
So as an attacker, gain access to an encrypted message, you know how long the message is going to be within a certain range.
That's right. Yeah, you will know that the length of the message, unfortunately. Yeah. So that there are several attacks that like we can actually launch by knowing the length of the message. But so to defeat such an attack, there's a way to like amortize all the length to certain bytes. For example, even if you encrypt 1 byte, 10 bytes, and then we always send 2 kilobytes of data. Yeah, that kind of thing is possible, but with the overhead of the network bandwidth. Yeah. So the sum of the database that would like to hide something. So it is so-called oblivious database. Yeah. So that they do use that kind of technique to hide the length as leak to the the attackers. But the ECB scheme is not perfect. Yeah, I want to introduce a weakness of the ECB scheme. Yeah, as an example. And then another important thing is that this ECB scheme is completely orthogonal to the algorithm of the block cipher. What that means is that we can use ECB with AES. We can use ECB with DES. And then there are another algorithm, Camellia or Seed. Yeah, we can use any kind of block cipher because conceptually block cipher encrypts a block by block. And then this kind of the block mode is the independent to the block cipher algorithm itself. Yeah, so make sure to know that. And then a weakness of the ECB is that, so the example was we don't want to exchange key for the multiple time, and then we just want to exchange one key and then reuse that for the communication. But the block cipher is deterministic. What that means is that for a specific key, if we provide number 1, the outcoming ciphertext will be fixed. Otherwise, we cannot decrypt it, right? So what that means is that for the same key, if we encrypt this string, then it will result in this number. So there's a direct mapping between the plain text and then ciphertext. So as an attacker, even if attacker don't know about what the plain text is, just say on the line, observe the ciphertext. And then suppose I'm sending either 0 and 1, but the sending so many 0 than the ones. Then there could be 2 types of the ciphertext, and then attacker might know which one is 0, which one is 1, depending on if they know that I'm sending more zeros than 1. Yeah, so that kind of analysis is possible. So what that means is that, so suppose message 0 is encrypted in this number, and then message 1 is encrypted in that number. Yeah. Then if I send this, then if attacker knows that I'm sending more 0 than 1, yeah, usually, yeah, then they can easily guess that's 1. Yeah, just based on just looking at the ciphertext, because there's no change in the ciphertext for the fixed key and the fixed message. So in the lecture in the next week, I will introduce how can we avoid this kind of attack by using some other different mode than ECB, because we don't use ECB in reality. Yeah, but I want to introduce this as like some of the historical, and then the let you know about like what are the insecure stuff. Yeah. Yes. So the summary for ECB. ECB stands for Electronic Code Book, and then it is there for detecting which part of the things are the real plain text and the padding. And the padding is required because we are encrypting the thing as a block. Yeah. So Block Cipher can encrypt arbitrary length data because we can add padding. And then padding scheme is that like we can get the padding size as a 16 minus size, and then get the remainder of the divided by size divided by 16. Yeah. So for the sizes like the exactly divided by like 16, then we will have the 16 length bytes of the padding. Yeah, that's what we saw in like the 1010 16 times as additional data. Yeah. So it could be burdensome to have like the one more block, but that could be small in this era, 16 bytes. Yeah. So like we may use like that kind of padding scheme. So for the exact size one, like we will have the 16 byte padding. So at most it will send the 16 byte more data than like the actual data. So if the message is long enough, then it would not be an overhead. But if you are sending just 1 bit information every time, then like the rest of like the 127 bits are wasted. So based on your communication pattern, yeah, you'd better use some other scheme for the sending smaller data. Yeah, in some sense. Yeah. So we will learn more about that when we learn about like a different mode of cipher that may work as a stream cipher. But the weakness of the ECB is that like using the same key will be fixed because the algorithm itself is deterministic. Yeah. So because that's the property of the permutation. So for the encryption, the decryption need to be the inverse of that like the operation. And then to have an inverse function, yeah, the domain and range size need to be the same, and then the function should be bijection, one-to-one onto function. Yeah. So that makes like everything need to be deterministic. Yeah. So if we have the same plain text, then it will be resulting in the same ciphertext. So to show the weaknesses in a picture, so this is the picture of the penguin for Linux. Yeah. And then if we use ECB mode, no matter what kind of the block cipher algorithm you use, if we encrypted this kind of bitmap with the ECB mode, it will be resulting like this. Do you think that ECB is secure right now? Not at all, right? So it may leak something like that because, so these are some of the white ones. So white ones, pixel value is up. So bitmap is all 0. Yeah. So the same thing will be encrypted as the same bit pattern. So that's why we have like the very uniform bit patterns for the background, and then somewhat random patterns for the other parts. But the difference between the uniform and the random, it will reveal some of the data of the picture. So I prepared one simple exercise for ECB, and then we will have more exercise releasing next week by learning for more mode of the block ciphers. So the exercise is very simple. I prepared one image that stores a flag, yeah, as a bitmap, And then I encrypted that with a random key. I even don't know the key, yeah, in Ecb. But if you open this one, then you will see the flag is something like this kind of format. Yeah. So please read what the flag is, and then submit it to our scoring system. And then I made a mistake. I used a capital CS for here. So the flag starts with the capital CS 370 and braces. Yeah. So please don't get confused about like typing the small case at here. Yeah. But you will see the like a cracked message in the bitmap format by connecting to this website. Yeah. And then that is the answer. And then like from the Zoom side, one student asked about what are the difference between AES and the RSA. So the AES is a block cipher, and then RSA is a public and private key crypto that is available for generating the digital signature. So it can do many more things, but the RSA is much slower than AES, and then RSA is insecure against quantum computers. So we will learn about the RSA next Thursday. Yeah. So please wait until like we learn about that, or like if you can't wait, please send a direct message to me. Then I will shoot some of the articles that you can read beforehand. Any other questions about the topics for today? And let me finish the lecture at here, and then I will stay in the room until 3:50. So like if someone wants to work on the some other challenges, you can stay here and then ask any kind of questions to me.